Hello, folks. We are back here for the lecture of Physics 122. And let me share with you what's the situation with the notes, okay? Okay, go. We just finished the second exam. And I also assigned homework for chapters 17 and 18. That's the situation right now. So let me document everything here for you. Go. So today is 31st of July, 2021. Okay. So I'm sharing the screen here with you. And one. Assigned homework for chapters 17 and 18. 17 and 18. Okay. Some of the videos for the lecture. Has already been downloaded. Have already been downloaded as videos, as lab videos. So the lab videos that we did are going to be used for the lecture. Okay. So here you go. Let's go through that. So motion of charges in a uniform field. We already have this video, and that's gonna be show up in exam 3. Remember that only part of chapter 16 showed up in exam 2, right? So you should expect 16.5, 16.6, and 16.7. We have videos on that, and I'm going to share with you what those videos are. Okay, so here are the videos that we have in my YouTube channel. Okay, so let's go back to the sections that you have to know for the exam number 3. All right, motion of charges in a uniform field. Let's see if we have it there. You know, is this one right in here? Okay, was uploaded on July 26. Okay, next one, conductors in electrostatic equilibrium. It's part of this one right in here. Okay, it's a short chapter. You can read that too as well. What else? Gauss's law. Okay, Gauss's law, section 16.7. Let's see here, uniform fields. Yeah, right in here, Gauss's law. The video's in there already. There's no view yet, right, for this video. What else do you need? Here you go. Electric potential energy. Electric potential, yeah, right in here. That's the one right in here. So has been uploaded, 28. Okay, electric potential is there as well. Section 17.2, right in here. .3 we're going to skip. And now what we're going to do is conservation of energy of moving charges. We're going to do this video. Take a look. All this information is in the notes, okay, in the lecture notes that I uploaded to the Google Drive. So let me just emphasize the ones that we need to do. Here we go. We need to do this one. We don't have a video yet, but we do have a video for those two. It was the video for the lab on the capacitors. We dealt with dielectrics, so 17.5 and 17.6 is a lab video that you can use as well. We are going to need a video for this one. Okay, those two are lab videos that we did recently as well. And resistance and resistivity. I'm going to do this video here. Okay, resistors in series and parallel, we did that. But we didn't do capacitors in series. Okay. Circuit analysis using Kirchhoff's rule. We need a video for that. And this one, we have a lab video as well. In RC circuit, you know, I'm going to need a video also. I'm going to do a lab for that as well. So let's start with the video on conservation of energy of moving charges. Okay. Let's go back here to the book. And that's the section we're talking about. So, you know, it's a rather straightforward session if you learn how to do problems, mechanic problems using conservation of energy. You're also going to know how to solve problems on conservation of energy of electric charges. Okay, so basically we have potential energy plus kinetic energy, and if it's conserved, if the energy is conserved, initial potential energy plus kinetic energy is going to be equal to final potential energy and plus kinetic energy. That's what we have in there. Okay, and let's work that out. Okay, here you go. The potential energy that you have right here is going to be just the electric potential energy. There won't be any gravitational potential energy because the mass of the electron, the gravitational potential energy of the electron, is negligible compared to the electric potential energy. Not just the electron, but the charges in general. Okay, so let's go ahead here and document here. Conservation of energy. Okay. Conservation of energy of moving charges. Okay. We can use the concept of conservation of energy to determine motion or position of electric charges. Okay. Okay, so consider an electric charge inside, for instance, an electric field. Okay, we have, in this case, we have a positive electric charge here, which is subjected to an electric field. We have already seen a problem like that. And we solve this problem in terms of forces. Okay, so this charge is subject to a force, and we solve this problem in terms of an electric force. But we can also do that using conservation of energy for electric charges. So what do you have here? In this case, we have this electric charge is initially at 0, velocity equals 0. Let's put that here. You go. consider that the initial velocity of this charge right here next to the positive plate is 0. Initial velocity. Initially at rest. So its kinetic energy is going to be 0 as well. Initial kinetic energy is going to be 0 as well. And let's say we have a non-electric potential difference between those two plates, right? So non-delta V. I'm gonna put that here at the bottom. Delta V. Here you go. Between those two, okay? So the question is what's going to be the final velocity of the electric charge here at the other end of the plate? Well, we can find that out by using conservation of energy. This is just an example, the simplest example that you're going to see out there for solving problems of conservation of energy for electric charges. Okay, so let's go here. We'll insert the equations for you. According to the book, initial kinetic energy plus initial potential energy must be equal to final kinetic energy plus final potential energy, like that. For that specific problem, the initial kinetic energy is 0. So you can erase that. Okay, I have also to state what is the electric charge of this charge, right? So let's say it's little q instead of big Q that the plate is. To go. At this very point here in the electric field, the electric charge has a potential energy due to the electric field, electric potential energy. And this electric potential energy is going to be given by Q delta V. Go Q delta V. Okay. At the end, that's the initial, right? after the charge has moved through the electric field, just like a object moves through the gravitational field, it loses potential energy. We can put the potential energy here at this end as being equal to 0. So here you go. We can illustrate the final position of the electric charge. Final velocity, right? The charge, the value of the charge didn't change throughout the motion. And I want to find the final velocity. Okay, at this point here, the charge spent all its potential energy, and its electric potential at this spot is going to be 0. Consequently, we are going to have the final electric potential being equal to 0. And the kinetic energy half mv squared. We have to know the value of the mass of the charge as well. Like that. We use concept of conservation of energy to determine, let's see, the velocity, right? Let's put the velocity of an electric charge. The velocity of an electric charge. Depending on the problem, you can also determine the position of the electric charge at a given spot in the electric field. Now we can solve this problem. Now 2 divided by m delta v squared is equal to that. We go. And we solve the equation for v. Okay, like that. 2 over mq delta v. That's one example of conservation of energy. Going back here to the book. That's what we have right in here. Okay. What we did is applicable to the electron gun in a CRT. Let's take a quick look here at this. In an electron gun, electrons accelerated from the cathode towards the anode. The cathode is the negative part of the electron gun, and the anode is the positive, right? Which is at a potential higher than the cathode. The anode is a higher potential than the anode. The anode is the positive. That's why it's a higher potential energy. A higher potential, electric potential. If the potential difference between the cathode and anode is 12 kilovolts, at what speed do the electrons move as they reach the anode? Assume the initial kinetic energy as they leave is negligible. Okay, so we're going to use that equation that you saw to find out the velocity, right? Here you go. At what speed? Okay, so here you go. It's delta V is 12 kilo electron volts. So going back here to this, the electron gun is something like that, right? So, but yeah, the charge is going to be negative, not positive. So let's do according to the problem. Electron gun. what we have here is a negative charge. Okay, here the charge is minus E. The initial velocity is negligible. Okay, so you can say that the initial velocity is 0. But how we illustrate this problem? Here we go. In real life, in a real life, you have a source of electrons here behind this plate, and this plate has a hole here inside. Okay, a small hole, so the hole doesn't interfere too much with the uniform electric field. When the charges are injected here through this hole, some of the charges go through, others don't. Okay, when the charge is injected through this hole and their velocity is negligible compared to the final velocity, they are accelerated from this spot to this spot. In this case, the delta V is what? Let's take a look. The problem is 12 kV. Delta V here is 12 kV. Accelerated from here to here. Going back here, you go. At what speed the electrons reach there, right? After it goes through this electric field, that's what she's asking. The book is asking. The charge ends up on the other side of the field of the electric potential. It spent all the potential energy, and here we have a little hole too again. In general, is in the middle of the plate. Okay, so the hole should be around here. It should stand a given distance, and the electron gets passed by this hole. Final velocity. Let's move that a little bit lower, so this electron is going to be close to the hole, right? Here you go. Around here. Yep. And the other is slide too, right? The electron should be a little bit lower. Here you go, right in here. So let's find out. Let's close this one here, and for an electron in a electric field, the electric potential difference is electric potential difference 12 kV. We have subjected, right? Having an electric potential difference. Potential 12 kV. Final velocity of the charge will be substituting the values. Q in this case is going to be E because it's an electron. The mass of the electron you can see there in the book. The delta V is going to be 12,000 volts. which is joules per coulomb, right? Joules per coulomb. The electric charge, what's the value of the electric charge? Going to the internet, let's go to the internet and find out, or just look here in the book. There you go. The electric charge, 1.602 times 10 to minus 12 coulombs. Okay. Here he's doing according to the signs that we have. So let's do that too. You know, put minus here inside. But okay, so here you go. Yeah, we do have a negative electric charge here. Let me put negative here next to this electron. So there is no doubt that the negative comes from the electron itself, okay? The charge itself. But what happens here? Okay, what happens here? You know, what we have here is a delta V, right? Let's put the delta V here instead of putting the actual value. And then we expand this delta V. Let's not put the 12,000 yet. So you can see that what's going to happen to the negative sign here. So this delta V, delta V is always what? V final minus V initial. Okay, so here we go. V final minus V initial. Okay, and this, you know, difference is going to be minus 12,000 volts. So now this negative sign cancel out with the other one. We gotta get the mass of the electron. Okay, and the mass of the electron is right in here, 9.1 times 10 to minus 31, right? And we get this speed that's very high. We calculate that something like that before, right? So that's how you solve problems. Let's go back here to my notes. Here you go. In summary, what we have is like that. Okay, is kinetic energy plus potential energy. You know, the potential energy can be written as the electric charge times the initial electric potential. Here is going to become the final potential, and we get a Q here as well. Okay, and then you substitute the equations in a proper way. That's, in summary, that's what we have. Half mv I squared, so vi squared the final square. Okay, so basically that's what this chapter is all about. You can do the same for a proton, and that's what we have for this section here. Okay, now we are going to talk about, we finish here with this chapter on conservation of energy of moving charges, right? So the next chapter is on capacitors. We already covered that before, right? We have the definition of something important called capacitance. Again, what's a capacitor? It's two conductors with opposite charges that have same magnitude. They create an electric potential difference because you have a separation of charges in there. Okay, and the definition of capacitance, which ends up being a very important definition, is Q over V, right? Q over, here you go. Capacitance is Q over delta V or V, amount of electric charge divided by the electric potential difference. And we saw before that we derived that the electric field for a capacitor, which is the amount of charge divided by the area and epsilon naught. Okay, and the electric potential is just the electric field. The electric potential of a uniform field, due to a uniform field, is just the electric field times the distance between the plates, which ends up being something like that. You substitute that equation in the definition of capacitance, okay? And we find that the capacitance of a parallel plate capacitor is epsilon naught A over D. But that's for a parallel plate capacitor. Other capacitors, the capacitance is going to be different. But the important thing to have in mind is that the capacitance is a function only of the geometric properties of the device, the area, the distance between the plates. Everything else is a constant. So the capacitance, unless you build the capacitor in a special way, if the dimensions, the geometrical configuration of the capacitor remains constant, the capacitance is going to be the same all the time. Okay, so here we go. That was covered before in our lab. Okay, so remember this definition of capacitance. We're going to need that later on. Okay, the capacitors has applications, for instance, in computer keyboards, and there are many other applications out there. You can look into that. Okay. A microphone uses a capacitor with one moving plate to create an electric signal. One of the moving plates vibrating in response to a sound wave. Okay. So that's another application of a capacitor. Dielectrics, we also saw dielectrics in our lab. Okay, so if you're talking about air and vacuum, the dielectric constant of air and vacuum is almost the same, But if you're talking about other types of materials, right? Here you go. The dielectric constant of air and the vacuum is approximately 1. A vacuum is 1. The air is a little bit more than 1, but you know, it's very close to 1. Okay, so here you go. Air, dry air at 1 atmosphere is 1.00054. But then we have other types of materials that has a dielectric constant higher than that. We covered that. We also covered about polarization and dielectric, right? When we put a dielectric inside a capacitor, a parallel plate capacitor, for instance, what happens to the capacitance? The capacitance increases by a factor kappa, by a factor of the dielectric constant. It's possible to prove that. Keep that in mind. We have polarizations in a plate, and that's what causes the dielectric constant to increase. It's it's the polarization in a dielectric that causes the capacitance of a capacitor to increase. Okay, that's the relationship between the dielectric constant, the field without the dielectric, divided by the field created by the dielectric. Okay, cells, by the way, cells that we have out there can be modeled as a capacitor, a parallel plate capacitor. like the case of neuron. The neuron can be modeled as a parallel plate capacitor. Inside the cell, why is that? Okay, it's not just a neuron, but any other cell out there. Okay, so why is that? Inside the cell, we have a buildup of electric charges, and on the other side of the cell, we also have a buildup of charges of opposite sign. And the cell membrane acts just like the dielectric in between. So here is like having a plate electrically charged and another plate positively charged, negatively charged, another plate positively charged, right? Outside the cell, you can have ionic solution in which we end up building up electric charges there on the outside of the cell. And it is this electric field that's built up here inside the cell that allows the cell itself to do work and perform the tasks that require for living beings. Okay, so we have this discussion here. Thunderclouds too can be considered as a capacitor. Okay, if you have a buildup of negative charges in the clouds, we have a separation of electric charges. The negative charges induces a positive charge on the ground, right? And we end up forming a capacitor, and not only a capacitor, but an electric field also here in between. And we have some energy, electric energy, between those two regions. So that's, and now we're going to talk about energy stored in a capacitor. We need that. We need the theory behind capacitance to cover energy stored in a capacitor. Okay. So let me give you a qualitative idea that was not covered in the lab, so I'm going to cover that with a little bit more of detail. Okay, let me give you an idea of how we have energy stored in a capacitor. Okay, so here we have a generic capacitor that is initially uncharged. It's not a parallel plate capacitor, it's just a generic capacitor initially of any geometrical shape. Because the capacitor is uncharged, this capacitor is uncharged, there is no energy in this field. You cannot do any useful task whatsoever with this capacitor. So what we have to do, we have to create an electric potential between those two pieces of metal. What do we do? One way to understand how we create an electric potential and how also we get a potential energy between those two devices is by imagining. Okay, suppose that it's possible for you to go ahead and get your hand, right? Shove your hand in one side of the capacitor, grab hold of some negative charges like we have here and transfer to the other plate, one side of the plate to the other. Okay, that's what I'm doing here. When I grab those negative charges that was initially in this metal, in this piece of metal, in the other half, in the half side of the capacitor, I leave behind some positive charges. The capacitor becomes positively charged. We have an excess of positive charges because I withdrew some negative charges from that piece of metal. Okay, and these positive charges are going to attract those negative charges, are going to prevent you from transferring those negative charges to the other side of the capacitor. Think about that. Okay, think about that. So now we have this piece of metal here, another piece of metal right in here. I go ahead somehow, there is a way to do that, but somehow imagine that you can get your hand inside this piece of metal, grab a bunch of electric charges, negative electric charge, move it from this device. As you move from this device, you're going to feel resistive force. This resistive force is the electric force of the positive charges that were left behind here in this capacitor. Now this capacitor is positively charged, right? And then somehow, coming to the other side, you shove those negative charges in the other half of the metal, of the capacitor. Here you go. Here you go. See, that's the electric force acting on those negative charges. You're doing work to separate the negative charges, to move these negative charges from this side of the capacitor to the other one. And when you do this work, you create an electric potential energy. Okay, so here you go. I show the negative charges on the other side. Now the left side of the capacitor is charged, right? Positively charged. Look here, positively charged. While you are moving the negative charges to the other side, it's still uncharged. But when we show the negative side charges on the other side of the capacitor, it becomes negatively charged, minus Q less than 0. In this process, you did some work and you store potential energy in this device. Okay, here you go. We have now this electric force between those two, but those two devices, those two metals, they are fixed in place. Okay, if you don't let them, if you don't fix them in place, they're going to move towards each other and they are going to become neutrally charged, and you lose all that potential, all that work that you did to charge the capacitor. So that's how you should look at this, as how you introduce potential energy into a capacitor. We do this type of thing in a very simple way. You don't have to go ahead and grab hold of negative charges and shove on one side of the capacitor and shove on the other side. No. There's an easier way of doing that. All you gotta do is to connect those metals to a battery. One metal is going to be connected to a positive side of the battery. The other metal is going to be connected to the negative side of the battery. Just by connecting those two different metals to the positive and negative side of the battery, you electrically charge them and you form a capacitor. Okay, so here you go. When you charge them, you create a potential difference between the capacitor, that's what this V is, between the plates of the capacitor, right? Between the elements of the capacitor. And we can calculate how much potential energy we create between those two. It's a little bit difficult, but is enough for you to understand how it is done. Okay, the book explains very nicely. Let's take a look here at the book. Here you go. So we have here an illustration, right? How you charge the plates of this capacitor is a negative and positive charge just using a battery. But a qualitative way of understanding that is just by imagining that you can collect negative charges on one plate and shove them on another plate. Okay. So, well, remember that there is that relationship for the capacitance, right? C equal to Q over delta V. And don't forget, C is constant. C is constant. Because C is constant, you know, we can plot the delta V over versus Q. It's a straight line. Okay. It goes according to that equation that you saw. Here you go. The slope is going to be given by 1 divided by C, right? This is slope here. Again, take a look at this equation. This is a linear equation in Q with a slope equal to 1 divided by C. Okay. So what we are doing, you know, we're charging this capacitor little by little, right? We get a very small amount of electric charge, you know, and on one side and shove on the other side. So we are, when you do that, this electric potential keep on increasing linearly with the amount of charge that you have. Okay. Keep that graph in mind. That's very important. The total energy transferred to the capacitor is going to be equal to this area right in here under the curve. Okay. Okay, so when you get just a little bit of charge, a delta Q charge, amount of charge delta Q, what's going to be the energy that your potential energy that you're creating? The potential energy that you're creating is going to be delta Q times delta V. Remember that equation? Electric potential energy is Q times delta V, right? So that's exactly what we have. The infinitesimal increase in electric potential energy, just like your book says here, is equal to delta Q times delta V. Okay? So as you progress in the charging of your capacitor, you're going to have a bunch of those little rectangles right in here. Okay? So this electric potential plus the next one, plus the next one, plus the next one is going to be the total electric potential energy that's stored in your capacitor. Okay? If you stop right in here, the capacitor is going to have less potential energy. But if you keep on charging and keep on increasing the electric potential energy and the electric potential, if you keep increasing the electric potential between the plates, your energy goes higher and higher. Okay? So because the delta V is not constant, we must calculate the potential energy by looking at the area of this triangle. Okay? And the area of this triangle is going to be what? Delta V times Q divided by 2. Okay? So we have to use this equation because the delta V changes as time goes by. Okay? So the situation is the following. So that's the procedure, right? For you to understand how we calculate the energy, the potential in the capacitor. So here, the situation is like that. Let me elaborate a little bit in that graph that the book did, okay? So here you go. Graph, horizontal line. And okay, here you go. So we start with a capacitor with a that is uncharged. So here you go. I'm gonna get this thing here. Delta V means the difference in electric potential between each plate. Okay? So here you go. I'm gonna put delta V here. Okay. In this axis, and Q on the other one. Right in here. Gotta put the units there, of course, right? So initially the capacitor is discharged. So that's how the story goes, right? Initially the capacitor is discharged. There is no electric potential difference. Electric potential difference is 0. And then we go ahead and get a little bit of electric charge out of this capacitor, right? Delta Q amount. And as we do that, we raise the electric potential difference there in the capacitor, something like that. because the amount of charge is very little, we can approximate, we can say that the electric potential remains almost constant. That's how we do this approximation, okay? We also know that there is a linear relationship between the electric potential and the electric charge, right? According here, it's gonna be a relationship like that. Go. Right? If I were to do in a better way, here you go. I would make it a little bit shorter like that, all right? Or even better, a little bit like that, you know, a little bit above, a little bit below. Oh. So in this first step, we have an energy, electric potential energy, that's going to be delta V times Q, or delta Q in this case, right? That's how you do it. I'm elaborating a little bit in that explanation of the book. In the next step, you know, I'm going to get some charges, a little bit more of charge, right? Almost the same amount. And the electric potential is going to be built up to a higher value. Okay. So now the electric potential, the energy or the energy stored in your capacitor is going to be this delta V1 times delta Q1 plus delta V2 plus delta Q2. Okay. That's how it goes. And then we do that several times, right? A little bit and a little bit, okay? You keep on doing that until you reach your electric potential difference that you want your capacitor to stay. Something like that. Like that. Go. Yeah. So the overall energy is going to be the area below this triangle, or the sum of all those small areas that you see here. Okay, and the area of this triangle is going to be given by half delta V over Q. That's how we can calculate the energy stored in a capacitor. Okay, and here you go, Q delta V. Let's write that down in my notes. Here you go, energy stored in a capacitor. Energy storage in a capacitor. The energy, when we talk about energy storage, we're talking about potential energy, okay? Energy storage. I'm talking about the potential, electric potential, the electric potential energy. Electric potential energy stored. So here we go. The net U is going to be half of Q delta V. Delta V, here you go. Delta V. Final delta V. Okay. So this equation can be rewritten in a different way using the capacitance of the device. Okay, so here we go, going back there to the capacitance definition is to keep, to stay consistent with the book. Let's put big Q here, right? The capacitance of the capacitor is defined as big Q divided by delta V, like that, right? So we can rewrite this equation a different way, just by using this relation. It's rather difficult to determine what's the electric charge that a capacitor is holding. It's very difficult to measure it. Practically speaking, it's very difficult to do that. So what we do, we write the charge in the capacitor in terms of its capacitance and the delta V, right? That's what we do. So we do like that. Q equal to C times delta V. So these equations are more useful ones instead of the previous one. Delta V is easy to measure with a multimeter, but the Q is more difficult to determine. So in general, we write the energy of the capacitor in terms of the capacitance and the delta V, because capacitance is usually written in the capacitor, and delta V can be measured with a multimeter. I'm going to substitute this equation right in here. Okay, so here we go. And then what we get half of C delta V squared. Like that. Looks just like the kinetic energy, right? Or even better, this equation looks like the potential energy of a spring, right? Half kx squared. So if you want to memorize this equation, just remember the equation for the electric potential energy of a spring. And then you can, of course, rewrite that in terms of the charge as well. The book that did that in terms of the charge, and here is the way that I did. Okay, so that's how we calculate the energy. Let's see this one. Let's take a look at this example. Fibrillation is a chaotic pattern of heart activity that's ineffective at pumping blood and is therefore life-threatening. A device known as the defibrillator is used to shock the heart back to a normal beat pattern. The defibrillator discharges a capacitor through paddles on the screen so that some of the charge flows through the heart. Here we go. 1734, that's the figure right in here. Okay, see here, one is the positive, the other is the negative, okay? And this charge are going to be discharged through the heart of the patient, and the current is going to flow either from here to here or from here to there, and it's going to pass through the heart. Okay, so we have this 11 microfarad capacitor is charged to 6 kilovolts, 6,000 volts, and then discharges through the paddles into the patient body. How much energy is stored in the capacitor? How much charge flows to the patient body in the capacitor if the capacitor discharges completely? Okay, here you go. Remember I told you it's easier to calculate the potential energy when you have the capacitance and the voltage. All right. So you gotta be half of CV squared, delta V squared. Okay, we go C delta V squared, and yeah, let's see here. And by the way, he's not taking into account the dielectric constant of the human body. Okay, so he goes. So that's why he has this much, C delta V, 11 microfarad. Yep, 11 microfarad, 6,000 volts. Yeah, 6,000 volts, and 198 joules. Now we can calculate the charge as well. We know the electric potential. We know the capacitance, right? Q equal to C delta V. There you go. And we get that many charges there in your capacitor before you discharge through the body, the human body. 0.066 coulomb. Okay. So the energy that we are talking about here is the energy in the electric field. Okay. So if you go ahead and calculate the potential energy in terms of the parallel plate capacitor, we get this relationship that you see here. Capacitance here is going to be, remember, is a function of the area and the distance between the plates. There is this constant here, and this K depends on the dielectric that's in between the capacitor. Okay. So what are you doing? Let's do that in my notes. I'll do that in the notes for you. Although it's going to be exactly the same that we see here. We go. We have this equation. Electric potential. Capacitance of a parallel plate capacitor is going to know. Energy stored in a parallel plate capacitor. The capacitance is going to be given by the dielectric constant between the plates. This dielectric constant is kappa. Greek letters. Go. Kappa. It depends on the area, depends on the distance between the plates. But it depends also on that dielectric constant, right? That we call the epsilon naught. He wrote that in terms of a K. I prefer to write that in terms of the epsilon naught. Right in here. Epsilon naught is 1/4 pi K. So do that when you're studying. Make sure you just don't look at it, right? You go ahead, pen into the paper, repeat it manually as you do that. 1 divided by 4 pi K is epsilon naught. I'm simplifying my notation. But what else do we know? We know that delta V is the electric field times the distance between the plates. Okay, so here we go for a parallel plate capacitor. Delta V is E times D, the distance between the plates. go ahead and substitute that right in here. ED. Between parentheses. Those values are between parentheses. So, good. Go on this guy here. Go. Next step. This E goes squared. It is also squared. Okay, D cancels D. This one here. Cancels this other one here. Okay. And he writes everything in front of in front of the E square. Right here. Okay, here you go. AD is what? Is the volume between the two plates of the capacitor. The plate of both plates of the capacitor has an area A, and it has a separation D. So A multiplied by D is the volume of the capacitor. So we can write that down. I'm not going to write that big V. I'm going to write that as a small v. Let's see if the book did that as well. Okay. Yeah, he didn't put V. He just kept the AD. Okay. I'm going to even put delta V, okay? Delta V is the volume. And finally, we can rewrite using the above equation. We can determine the energy per unit of volume of the capacitor. And now that you know how much energy your capacitor has, now you can start planning, right, what your capacitor can do for you. Like do some type of useful work, right? If the useful work requires X joules, you're going to charge, you need to charge your capacitor to a voltage that will allow it to produce X joules of work. So here you go, I'm going to write U over delta V. And we get the simple result, kappa epsilon naught E square. The stronger the electric field, the more energy per unit of energy you have there. And also the more energy per unit volume you get as well. That's what we get, kappa epsilon naught E square. Okay. Now, very important, you know, even though derived above equation for a parallel plate capacitor, this energy density this equation of the energy density is good for any capacitor geometry, whether it's cylindrical, whether it's spherical, whether it's your genetic two blobs, two pieces of metal, right? Next one another. So that's what we have for this section. And we're going to move to the next one. Oh, let's see here. That's what we have for this chapter, by the way. Again, like I said, that's what we have for this chapter number 17. You have everything that you need to study. You have to combine those lecture notes with your lab notes, and you follow with your book as well. Okay, so let me know if you have any questions, and we'll now start on chapter 18. I see you soon.